All right. Good afternoon. Welcome everybody to the NAL First Thursday virtual program. Today is February 2nd, Groundhog's Day. Let's hope we don't have another repeat of the challenges that we've already had today. And my name is Lisa Spence. I have taken over from Stokes McMillan the auspicious task of hosting the programs for NAL for this year. Our speaker today is going to be Mr. Bradley Cheetham. Bradley is a lifelong space advocate, a highly experienced engineer, a three-time entrepreneur, and seasoned graduate level instructor. He's best known as the co-founder and CEO of Advanced Space, where he leads the company in its efforts to enable the sustainable exploration, development, and settlement of space by delivering solutions in flight dynamics, technology development, and rapid turnkey missions to clients across the space industry. Advanced Space is the owner and operator of the CAPSTONE spacecraft, which successfully arrived at the moon in 2022 as a pathfinder for NASA's Artemis program. Bradley serves as the PI for this mission, which represents the first ever commercial spacecraft to operate at the moon. And we're going to hear about the CAPSTONE project today. Mr. Cheetham earned a degree in aerospace engineering and mechanical engineering from the State University of New York at Buffalo and received his master's in aerospace engineering sciences from the University of Colorado at Boulder. There, he also conducted significant research on spacecraft navigation at the moon in support of his Doctor of Philosophy under the guidance of the late Dr. George Bourne. He created and taught a graduate level course in commercial spaceflight operations at CU Boulder for 7 years. As an advocate for the space industry, he was a co-founder and currently serves as the chair of the board of directors for the Future Space Leaders Foundation, is a member of the Entrepreneurship and Investment Committee of the International Astronautical Federation, and serves on the Board of Advisors and the Board of Trustees of Students for the Exploration and Development of Space, or SEDS. So I would like to, at this time, welcome Mr. Cheetham and turn it over to you.
Thank you for that kind introduction. I've got some of that content here in the presentation, and I'll be honest with you, Lisa, I don't think I could have said it better myself. So thank you for that. Just so we're doing technology here, can you check and tell me if you can see my slides?
Yes.
Great. All right, let me just move a couple of things here so I can see them. Great. So thank you for inviting me, first to Stokes and then to Lisa for making this happen. Very excited to be joining you all today. Wish I could be joining you in person down in Houston. It sounds like a little warmer down there than here, although you guys might not believe that based on what you're used to. But we were just talking beforehand, it's been a little chilly up here lately. So what I'm excited to share with you today is a bit about our journey to the moon, our capstone mission, which we're proud to call Small But Mighty. I'll talk a little bit about myself, a little bit about our company, and then we'll get into some details about the capstone mission itself. Look forward to, at the end of this, having some time to take some questions from you all. So I'll try to get through it at a good speed, but not spend too much time on any one topic. So just to start off with, bottom line up front, what are we talking about here? The capstone mission, capstone spacecraft, is a 12U CubeSat, so about the size of a microwave oven, if we're going by what we're allowed to say and approved to say, or what I think is more relatable is about the size of a case of beer, would fit on your desk, and we'll show you some pictures of it later, that has been operating in a near rectilinear halo orbit at the moon for 79 days as of today. This spacecraft launched in June of last year, late June, and it arrived at the moon on November 13th. We'll talk about that journey to get to the launch pad and then to get to the moon later. The mission itself serves as a pathfinder for NASA's Artemis program. So learning things by doing a rapid small spacecraft demonstration. And in addition to learning to support Artemis directly, the program is a technology demonstration activity for some enabling navigation technologies, as well as really pioneering what small spacecraft can do to support exploration and science missions. And finally, as Lisa mentioned, the CAPSTONE mission is led by our team here at Advanced Space. And we actually, the way the contract is set up, we own and operate the satellite. So that makes it the first commercial satellite to operate at the moon, and something that we're really proud of pathfinding as we are doing that to support our NASA and other partners. So Lisa, thank you for the great introduction. I just wanted to make sure we had something about me here. I think you covered pretty much all of this. I'll just say, I learned what cold and snowy could be when I was at the University of Buffalo for 4 years. Besides studying, not much else you want to do when it's that cold. So it's probably good to get through my double degree in aerospace and mechanical engineering. During my time there as an undergrad, I was really fortunate to be a member of the NASA Academy, which was a program at the time that was located at Goddard Space Flight Center. As part of the NASA Academy, we were introduced to leadership at NASA headquarters and traveled around to various centers, including Johnson Space Center, where we went in the middle of summer, and at the time, owned one suit, and it wasn't a very light suit or a very comfortable suit in the heat and humidity that you all are used to there. So that was a kind of exposure at a high level to all parts of NASA, a really formative experience. It was also an opportunity for me personally to work on the Artemis mission, which was actually the first mission ever to fly spacecraft in Earth-Moon three-body orbits. This was led by Goddard and UC Berkeley as an extension to the Themis mission. Those spacecraft are actually still operating at the moon, but that really gave me exposure to two really important things for the rest of this story. So one of those was astrodynamics and satellite navigation, orbits, specifically three-body orbits at the moon, which became the basis for my PhD research. And these spacecraft are also relatively small spacecraft. And so this also gave me some exposure to what's possible in small form factors in terms of what we can do in space. After graduating from the University of Buffalo, I was very privileged to get recruited and selected by Dr. George Bourne to come to CU Boulder. I completed my master's there and was working on my PhD research and had sort of left that all but dissertation, as we would call it. But Dr. Bourne really informed a lot of what I did, both in academia and also afterwards. I threw in here, he got his PhD at UT Austin and worked at the Manned Space Flight Center from 1968 to 1970 before he went to JPL, a quick stop back at UT, and then came to Boulder to start the Center for Astrodynamics Research, which is really the basis for the technical work that I was doing here. After spending a bunch of time studying how to do things at the moon and specifically navigating satellites there, really turned my focus to Advanced Space. So as a co-founder and CEO here at Advanced Space. We'll talk about that in a minute. One of the big drivers through this whole thing has really been a passion that was ignited by the incredible programs of the past to do things in space. And so this is something that, as long as I can remember, was always a driver and a motivator for me. As Lisa alluded to, also I'm the chair of the Future Space Leaders Foundation, which is an organization that exists to give scholarships to young professionals and graduate students to help bring more young talent into the industry. And also proud to be a member of the Board of Trustees for the Students for the Exploration and Development of Space, where it's one of the largest student-run student organizations supporting space in the industry. And then finally, principal investigator for the CAPSTONE mission. So I'm excited to share that with you. And then obviously, most importantly, husband and father to 3 little boys that are 5, 3, and 10 months old. So bear with me if I can't find a word tonight, because I had one of those guys keep me up part of the evening last night. Oh, I also wanted to say, hopefully this resonates with the audience here. I'm also, I grew up in the Northeast, but as I've moved out west, really a believer in the power of sort of cowboy ethics as a mantra, something that recently I was very fortunate to be able to attend at the rodeo at the National Western Stock Show here in Denver and ride on top of a stagecoach. Happy to take questions about this later, but I will tell you that it is fun and terrifying. That's not the most comfortable place to ride around an arena with horses pulling you. It's also not the smoothest of rides to take. So it's just kind of a little bit again about me, who's talking to you today. Now I'll talk a little bit about Advanced Space before we start talking about the CAPSTONE mission. So for us, and I think this was part of the introduction as well, I started with my co-founders Advanced Space over 12 years ago now, really with the vision and the purpose to enable the sustainable exploration, development, and settlement of space. For us at the time, we weren't billionaires like other people who had started companies around this time. So instead of building rockets to get to space, we focused on building orbits and software tools to get to space. And that sort of really this vision has driven us, and it drives us how we build our capabilities and how we execute our programs. Sort of trying to capture what does that mean in a visual. This is an old graphic that we've had that we keep around that I kind of share with my team as the reason why we do what we do here at Advanced Space is to create a future where people are living and working in space permanently. I show this as a mental experiment that I am excited that we're hopefully laying the groundwork that someday in the future, children, grandchildren, great-grandchildren, whatever it is, will look up at the moon and will be able to see the impact of people living and working there. As this is probably a fairly technical audience, I will admit that it will probably, yes, be underground and it will probably not look like this, but the idea is really to capture the excitement of someday, every human on Earth will be able to look up and see people's impact on the moon. I think will be a very transformative era when people know humanity is spreading into the solar system. What do we do at Advanced Space? So we'll talk about our mission later, but we have sort of three specialties in terms of how we fulfill our purpose and our vision as a company. We break those up into flight dynamics. Basically, we help people fly spacecraft. We help with constellations in low Earth orbit, a lot of subject matter expertise in electric propulsion or low thrust propulsion, cislunar between CAPSTONE and some other work we're doing, very important to us, as well as interplanetary. So we support projects going to other planets and evaluating how to do exploration missions maybe differently. So that's sort of the foundation. On top of that, we build a lot of efforts in technology development. For us, what that means is building capabilities that will enable flight dynamics in certain areas like onboard spacecraft automation, as well as infusing the latest in artificial intelligence and machine learning to really enable the future of space operations that we see could very quickly and very easily be limited by the available bandwidth and the tools that we have right now to fly spacecraft. So this is really our focus, is how do we get to a future where spacecraft operations are proliferated and are safe and secure and transparent, and we are able to go execute those missions. And finally, we build sort of those two on building on flight dynamics, building on some of the novel technologies we have. What we have is sort of third area we call rapid turnkey missions. The best example of this is CAPSTONE, which we'll talk about in a minute. But this also looks like taking questions about, what would it take to fly a certain mission to a certain location, trying to basically understand what systems can handle and how to design end-to-end missions, understanding, the propulsion systems and the launch vehicle systems and all these things have really changed a lot, and there's a lot of options. And so we really focus here on how to put together those emerging options to optimize missions for a variety of customers. Our team is mostly based here in North Denver, Colorado. We have some folks spread around the country here and there, but really our team is based here and is growing. As I was putting this slide together last night, we are up to about 45 people on our team now, and this picture barely captures I think about half of them. So I had to schedule a time to get a group picture because of putting these charts together. So that's, again, a little bit about me, a little bit about our company, but I think what's probably most exciting would be to get into some conversations about CAPSTONE. We've used that acronym a few times now. So the first thing, as any good aerospace engineering presentation, we'll define the acronym. So CAPSTONE is the Cislunar Autonomous Positioning System Technology, Operations, and Navigation Experiment. We did spend a lot of time to get a good acronym here. I'll have to admit that we had a whiteboard to work on this for a while, and it really came together between two thought processes as we built the program. The first four letters of the acronym CAPS is a technology we've been developing for several years. We'll talk about a little bit more in subsequent charts, but is really focused on how to enable navigation at the moon to scale and to be efficient in the future. And then the last four letters is the Technology, Operations, and Navigation Experiment. This really gets to how are we flying a small satellite that's going to inform and enhance future missions just from its existence of flying, not just the technologies that are on board. And so just, we've got engineering drawings and stuff coming up of the spacecraft, but just so you can get a sense of scale, the picture here that you should be seeing on the right, myself all the way on the left, our congressman next to us, next to me there, obviously Pam Melroy from NASA, and then on the far right, our director of engineering here, Tom Gardner. We are sitting behind the full-scale model of the spacecraft. So as we see pictures of the spacecraft coming up, you'll kind of have hopefully a sense of the size, something that one or two people can carry around, can move, can pick up, and this is the 1-to-1 scale, so not a reduced scale model. We'll talk about some of the key components of that the spacecraft itself coming up. So as a summary, the CAPSTONE spacecraft is the first CubeSat to fly in cislunar space. It's also the first spacecraft to enter into the near rectilinear halo orbit, or NRHO, which is where the plan is to put the lunar gateway. As a mission, as a pathfinding mission, we're really focused on helping to reduce risk for future spacecraft. So we're validating navigation technologies both on board and on the ground, as well as verifying dynamics and assumptions, and making sure that the operations in the NRHO are well characterized, whether that means the assumptions that we make on orbit determination accuracy or minimum number of times we're going to have to fire the thrusters. There's just a lot of pieces of this which we certainly can model and have modeled, but getting to flight illuminates and helps us understand things we might not have thought about otherwise. One of the key things for CAPSTONE as a pathfinder was that we had to move quickly. This was a priority from the beginning of the program. As it were, we went from concept to launch in about 33 months. That was longer than we had wanted, but is quicker than I think a lot of people thought we would be able to accomplish. After launch, we had about a 4-month transfer. So this wasn't a 3-day transfer like we saw traditionally. This was a 4-month transfer using something we call a low energy ballistic lunar transfer. Hopefully we're far enough away from lunch that mentioning BLT isn't too distracting. But that got us there very efficiently, and that was really an enabling design consideration to do this mission in a small spacecraft form factor. And then the mission itself, again, I mentioned we've been there 79 days. The baseline plan is to operate at the moon for 18 months, and over that time, continue to learn and demonstrate new technologies. As it relates to the actual objectives, and these are all broken out into measurable objectives, as you can all imagine, that I didn't want to necessarily bore you all with, but we have sort of 3 high-level mission objectives. The first of those was to validate and demonstrate the 3-body Earth-Moon operations, both of the spacecraft itself, but also certainly of the ground segment and the software here on Earth that we're using to fly the spacecraft and to do the flight dynamics operations. That was our first objective. Our second objective was to inform future lunar exploration requirements and operations, such as for the Artemis program's lunar gateway. So this gets into the idea of looking at, okay, what kind of navigation accuracies are reasonable? How does that flow into station keeping budgets? What kind of stability can we expect when we're actually flying versus when we're designing these things in simulations? And then our third objective is to demonstrate and accelerate by demonstrating the infusion of the cislunar autonomous positioning system, or CAPS, as I mentioned before, which we think is really a potential enabling technology for future missions at the moon. As we see more and more spacecraft there, the demand for the ground tracking sources and the finite resources to fly them, we think will quickly be occupied. So we think that's really an enabling technology. So here, I just want to pause for a second and mention sort of, we get the question sometimes, why fly a Pathfinder mission? And I'll say that one of the key purposes here, I think, is really captured in this Hugh Dryden quote. The purpose of flight research is to separate the real from the imagined problems and to make known the overlooked and the unexpected. What we have seen as we've flown the program, and I have a chart at the end on some of the challenges that we had to overcome, is really that there's a lot of things that you can anticipate and model, but there's also a lot of things that until you go and file the paperwork to launch a spacecraft, or you go build the plan all the way to operations, there's a lot of things that don't necessarily come out early on that you can plan for and predict. And so I think, you know, we've intentionally uncovered some things that we didn't know that helped, and I'll say, and I'll refer to this later too, but we've also unintentionally uncovered some things through anomalies and through other challenges that we had, that certainly have taught us lessons. Some of them certainly more stressful than others. So as promised, here's some more technical design details of the spacecraft. Again, one of the big challenges here is we're doing a lot in a relatively small package. So I'll just call out a few key things. One of the enabling demonstrations that we're working to do with CAPSTONE is to do a first of its kind cross-link with the Lunar Reconnaissance Orbiter. One of the foundational data types for CAPS is a peer-to-peer crosslink, where we will send a signal to the Lunar Reconnaissance Orbiter, and then LRO will send that signal back to us. The CAPSTONE spacecraft, from sending and receiving that signal, will get a data type, and from that we can actually estimate the state of both spacecraft, not just where they are relative to each other, but where they are absolutely in space. And so that's a key kind of consideration for CAPSTONE, and also for the CAPS system underneath it. And that is the antenna you see here in the top left. I'm not sure if you can see my pointer, but it looks kind of like a pizza box here on the top. In the configuration on the left, we'll see the spacecraft is actually how it looks stowed, ready for launch. The spacecraft was launched in a dispenser, a kind of 12U dispenser, so that allowed us to isolate a lot of the loads from launch. So the spacecraft system itself didn't have to take those loads, but the dispenser would. And then after launch, as we got into orbit, we separated out. As you can see, the antenna that I mentioned, the pizza box shaped antenna on the top, sticks out of the traditional 12-unit CubeSat dispenser. And so that has led some to call us a 12U XL satellite, and not just a 12U, because we are a little longer than a traditional 12U would be, which was helpful because in that structure underneath the antenna is where we had all of the power amplifiers and radios to be able to do the communications experiment. So that extra space was fully utilized, as you can imagine, fitting a lot in a small package here. If we look at the middle picture here, again, this is sort of the stowed configuration, but just from a different angle. You can see we have our star trackers for attitude control, the S-band antennas we use for the cross link with LRO. We also have X-band antennas, which is our ground contact link for transmitting and receiving. We have an imager, and then in this picture, we also see the deployable solar arrays that are stowed. And then finally on the right, we see the spacecraft as deployed, our two arrays deployed out. And then on the back side here, you can see our thrusters, the thruster system, a key enabling technology for CAPSTONE, for both moving around and changing orbits, but also for desaturating our momentum wheels. That thruster configuration in the back is an 8 thruster configuration. So we have 4 axial thrusters and 4 rotational thrusters, and that has helped us get to the moon and to operate at the moon. Has also given us some challenges I'll talk about later. So some of the key considerations, as we, that's what was the design of the spacecraft, but getting from a design to flight, certainly there's a lot that goes into that. The first key consideration I alluded to earlier is schedule. So as we kicked off the program, one of the key observations is to be a pathfinder, you have to be ahead of the things you're pathfinding for. So it was very important to us that we had as much focus and discipline as we could on schedule, because that was really a core reason why we were doing the mission. If we were delayed multiple years and ended up flying late, we would lose a lot of the utility of actually flying the program to begin with. So I sort of put in context here for what that looked like. In reality is that we went from literally like a napkin idea to the kickoff of the program in about 6 months. This was formulated very rapidly and innovatively to get it going that long. So from the idea of can we fly a NRHO demonstration mission to the contract is signed, took 6 months. And then our initial target from that kickoff, that contract signature, was to be ready to launch in 18 months from when we started. Certainly very aggressive, not unheard of in the industry in the past, but something that at the time was certainly going to stress a lot of people out. And so to get that done, we were on a pretty good track from signing and kickoff to our system requirements review. Took about 30 days. From kickoff to PDR was about 90 days. From the kickoff to CDR was about 180 days. So we were on track to what we thought we needed to do. And then March of 2020 happened, and we were kind of hit with the unexpected challenge of global pandemic, and a lot of in-person meetings got canceled. A lot of issues happened in the supply chain, so that certainly slowed us down. And through that process, we uncovered some other issues. But as it relates to the schedule, we ended up hitting about 33 months, which is something again we're very proud of. We had a lot of focus on schedule, but also a lot of challenges that we didn't anticipate. Another key consideration that was built into that schedule of what's possible was that we really wanted to focus on leveraging existing commercial systems. And so the goal here was not to develop a new, bespoke, beautiful cislunar spacecraft. The goal was, what can we take that already exists, that people are already flying, and then add only what we have to add to go fly at the moon. Another key consideration, which was a muscle that we had to flex a couple times in the program, was we also had a mindset of continuously doing an analysis of alternatives for systems and designs. What that looked like in reality was that a couple of subsystems ran into problems during the program. Either there were development items that ran into issues, or just performance of what was predicted didn't meet what was planned. And in both of those cases, we were able to very rapidly mature sort of backup capabilities that had performed and had got us to the launch pad and got us to space. That was something certainly that was, I think, somewhat novel in the context of how we were doing it, and I think also was something that helped us to really stay focused, because we didn't have the excuse of any one subsystem being behind, and therefore every other subsystem could take their foot off the gas, because we knew we had to push and had to maintain focus on that schedule. Another key focus was a rapid iteration, sort of going hand in hand with continuously evaluating alternatives. We had to be able to quickly iterate through designs, mature designs, and then move forward. And finally, the probably the most important consideration was that it was really a team effort. So certainly we were leading the program, but our NASA partners, both all over at NASA headquarters, at NASA Ames, at folks at JSC, at JPL, other places. We had the Launch Services Program from Kennedy. It was really a team effort, really a team focused effort. And so there was a lot of times where things came up and different people would get involved to help. And we certainly would not have gotten to the moon without that team focus. And then some of the things we didn't account for, global pandemic was, I tell people that was not part of our statement of work. So that was obviously caused a challenge for us. We also had some issues where we ran into technology gaps. And so that in a couple of places, that was technologies that were expected to be matured, and it turns out when we started working with them, they were not as mature as we thought. That also looks like things where there were variations in taking a technology that has worked maybe in low Earth orbit and applying it to a cislunar, to a lunar mission, where there were some gaps that were surfaced. And then finally, one of the other key things that we didn't expect was unknown unknowns. And this gets to things like regulatory lead times for filing certain things, where, as an example, the frequency licensing process, they'd like you to start 18 months before launch. And so when we started it around PDR, we were already late, but our whole program was 18 months, and that just wasn't how the processes were set up. So we uncovered some of those long lead activities that were not necessarily hardware driven. But we got through those challenges. And here's some pictures of the spacecraft ready to fly. The left is actually the flight unit. So you can imagine people for scale based on the picture from earlier. The middle picture is the CubeSat spacecraft again in its container, looked wrapped kind of in tinfoil here for thermal reasons. But this is it attached to the upper stage of the launch vehicle. One of the interesting things is as a CubeSat, traditionally, these small spacecraft, are ride shared, get kicked off a big rocket after a primary payload has been deployed. One of the interesting things for Capstone was we were actually the only payload on a dedicated Rocket Lab rocket launch. And so we are, in this picture, this is the upper stage of the launch vehicle. We are the only payload on board. And then again, for scale, you can see after the fairing had been put on there with the NASA worm and the mission logos. That's the team at the integration site in New Zealand that put together the system and got it ready for flight, just to kind of give you a sense of scale. One of the other things to rewind back to that time, New Zealand, as you might have read in the news, was one of the toughest places as it relates to COVID. They had a very tight procedures, and so one of the challenges we had was just getting not the spacecraft getting in was actually relatively easy, but getting the people that we needed to get in to service a spacecraft and get it ready for launch was a pretty non-trivial risk and a process that we had to manage throughout the program. And as it relates to that, thinking about the actual flight of the spacecraft, which I'll show a video of coming up, the only people that were actually down there for that were the integration teams, because we, due to COVID protocols and restrictions, we couldn't go down there to watch the launch ourselves. So this is the spacecraft ready to go. And we launched early morning for Eastern time, about 5:55 a.m. On June 28th. It was an incredible launch, beautiful night launch from Mahia, New Zealand. And so this is on a peninsula in New Zealand that is where Rocket Lab's primary launch operations are conducted out of. And we'll try this to see if the video will play through Zoom. Bear with me for just a second. And so I'll just, kind of talk through this, just so you have some idea. The upper stage that is launching the spacecraft has never flown before. This is the first time we've rolled it to the pad and got it ready. And I would have bet any amount of money that there was no chance this was going to go on the first try. So as that flame came out under the rocket, I was sitting in a hotel room watching it, and I was just totally awestruck that we were on our way to space. And it was actually quite incredible feeling, as probably many of you can relate to see all that hard work, all those late nights, all that working through the weekends pay off to get to a point where we were on our way to space. And so from this point on, the spacecraft, the spacecraft actually stayed attached to the upper stage for a few days. We separated from the upper stage of the launch vehicle on July 4th. And so obviously we're very excited to have our independence from the launch vehicle on the same day we celebrate the country's independence. As we separated out, and this is the plan, and basically as flown, we separated from the launch vehicle. We had several trajectory correction maneuvers, or TCMs. From the point of separation on July 4th, the spacecraft itself was in control. Its thrusters were directing the spacecraft to get on its mission to the moon. So we flew out here, obviously well past GEO, and in this case, well past the moon's orbit. Our apogee, or furthest point from the Earth, was on August 26th of last year. We reached over 1.5 million kilometers from the Earth. Along the way, kind of tweaking our trajectories, doing small maneuvers. The figure here is actually showing three different colors. If you can look closely, that's sort of the opening of the launch period, the middle of the launch period, and the closing of the launch period. And so what you can see from this is this allows us to launch. Had we not been able to launch at the first try, we had several other attempts, and this allowed us to have flexibility where no matter when we launched in that period, during about the 4 months of the transfer, we would always arrive at the same time under the same conditions. And so this was a key consideration as we optimized the mission itself. So we see here we've got we executed 4 trajectory correction maneuvers. We actually had a couple other maneuvers towards the end here that we didn't need, that we sort of built in to plan in case there is a need to do a correction or change or targeting. But as we were flying the spacecraft, turns out we did not need those correction maneuvers, so we didn't do them. We took them off. And so this kind of shows that transfer. Certainly, we in this case trade the time it took to fly, much longer than a direct transfer, but really traded off for the fuel required to fly it, as it's architected for Orion program missions to get to NRHO, requires powered lunar flybys and 2 or 3 times as much fuel to get into an NRHO if we were to have flown it directly. And as I mentioned earlier, this approach fundamentally to get to the moon is what allowed us to do this demonstration in a small 12U CubeSat form factor. Had we been doing something like a direct transfer with a powered lunar flyby, we would have had a significantly higher amount of fuel required, and probably would have driven us to a bigger spacecraft that would have added complexity, obviously, to the program. So this was as an orbit someone with an orbit background, something that we were proud of, is that we were able to, using this transfer approach, get to the moon very efficiently for the CubeSat demonstration. And then this, if we'll be able to hopefully get it to work, we'll show you here in red. If you can see, we have the CAPSTONE spacecraft coming in. This is what it looked like to arrive at the moon. Here in the foreground, the Earth, you can see the back spinning in the background to kind of give you a sense of time. We had to do our first part of our insertion maneuver there at our close approach to the moon. We had a second maneuver, which we called a correction maneuver, a couple of days later, and then a third one. And then from that point in time, we were in the near rectilinear halo orbit. And then this simulation also shows kind of what would have happened if we had not done that insertion maneuver. You can see it would have flown by the Earth and then departed back out into space. So this was our several moments of terror, if you will, for this critical maneuver that needed to happen to get into orbit, and then the cleanup maneuvers here that we had to do, and all was executed successfully. After a few days in orbit, we were able to confirm a full orbit of the near rectilinear halo orbit, and really kind of sigh a pretty significant sigh of relief on that activity. Just to provide a little context for the orbit that we're in and why we're in that orbit, the near rectilinear halo orbit, or NRHO, is a very specific orbit optimized for a lot of different considerations. This is the baseline for the Lunar Gateway. It is a quasi-stable orbit, and so this allows us to minimize the propellant required for orbit maintenance, but also makes it relatively affordable from a fuel perspective to get into and to get out of the orbit. If you look here on the right, this Earth-Moon pulsating, rotating frame that we have here, this really shows what does that orbit look like if you were looking from the Earth to the moon and you were able to follow your line of sight around with the moon. And so from this perspective, you can see we're continuously in view of the Earth. So we don't have any periods where the spacecraft is behind the moon, and therefore we'd have communications blackout periods, which is a key consideration. Another a big one that is not always obvious until you start thinking about operations of a satellite and requirements for a satellite is that this orbit is specifically designed and phased. So it's not just the orbit that matters, but also the timing. This orbit avoids significant eclipses and minimizes other eclipses. And here what we're talking about is really the fact that at this distance, moving through the Earth's shadow, if we were to do so at a worst case scenario, can result in an eclipse of several hours in duration, which for really any spacecraft that needs to worry about functionality, that's an incredible power system requirement, and really ultimately gets to the thermal subsystem. Another key consideration when we're at these distances is in low Earth orbit, even when we're in eclipse every 90 minutes, relatively short, but we also have some residual heat that a spacecraft is able to get from the Earth, even when it's not being illuminated by the sun. Conversely, out here at the moon, we get incredibly cold during eclipses. And so really our concept of operations, in order to survive, we have about 70-minute eclipses is the worst that we have in this phasing that we have at the moon in this orbit. Certainly much better than 8 hours. This is much more analogous to what spacecraft at GEO would experience. But we really end up going into basically a power conserve mode, power down everything, turn on heaters, and in some cases preheat components of the spacecraft, so that during that eclipse, as things get very, very cold, we don't hit any thermal limits with the subsystems. So that eclipse consideration, something that is not probably not the first thing people think about when they think about orbits, but to have an 8-hour eclipse would be incredibly challenging from a systems engineering perspective. The other key consideration for this orbit, as you can see kind of in this, again, in this far right figure, the orbit spends a lot of its time below the south pole of the moon. In fact, has visibility to the south pole over 95% of the time. So for future systems that may be going there to support relay communications, et cetera, for South Pole missions, incredibly beneficial from that perspective. The orbital period, or sort of quotes here, orbital period, the amount of time it takes to go through this one NRHO is about 6.5 days. So we have about an orbit a week, if you think of it that way. As we get close to the moon, our paraloon, or our closest approach to the moon surface, is about 3,500 kilometers, and then our apoloon about 71,000 kilometers. So you see sort of we're spend a lot of time as we kind of come down in that bottom part of the orbit. This is a 9-2 resonant orbit. So this again gives us repeating geometry, and you can see here in the inertial frame, and I have an animation coming up if we can get it to work, that will show you that the spacecraft is basically skirting above the moon and then going below it as the moon is orbiting the Earth. And let's see if the animation can help kind of visualize. A lot of times we see it in this rotating frame. It looks like a closed orbit around the moon, but it's all about your reference frame, obviously. Oops. So this is an animation showing how does that NRHO look with the Earth in the center. If we can get it to start. As it goes around, we have effectively an orbit that for a few hours every week is a low lunar orbit, and for the rest of the week is really just a high Earth orbit. And as I go around here and see, we sort of create this, we call it a crown, the orbit path that goes around the Earth here. We kind of refer to it like it looks like a crown. The key challenge for operating this orbit is exactly what I just said, that you are a lunar orbit for, we'll say, a day or less than a day, and then you are a high Earth orbit for about 5 or 6 days. And what we see is that as you come into that lunar close approach, the dynamics on the spacecraft are highly varying as you shift from being a high Earth orbit to a sort of a low lunar orbit and then back again. And that's where, from a navigation perspective and from an operational perspective, we have a lot to learn and improve as we optimize the operations here. And that ends up materializing in decisions such as doing station keeping maneuvers actually when we're furthest away from the moon. They would be more efficient if we did them close to the moon. But one of our challenges is that any error in an execution of a maneuver close to the moon is significantly amplified in the dynamics. But if we do those maneuvers later on in the orbit when we're further away, we have much more, the errors are not as compounded as they would be as we were closer to the moon. And so that's what we have been doing. So as I mentioned, for 79 days, we've been flying that orbit, demonstrating the operations, learning a tremendous amount. But a key factor for this program has been also to be a technology demonstration program. And so here's where we have some content that I wanted to share with you, just about what is that foundation that we're trying to lay. What does that look like? And so as it relates to pathfinding to support those missions, some of the benefits already for CAPSTONE included informing subsystems and performance for Artemis 1 secondaries. We're carrying an IRIS radio, which was on a lot of the CubeSats that flew along with the Artemis 1 launch. And so we were able to, through our testing and our demonstration, learn a lot about those radio operations, learn about unintentionally learning about some issues that operators needed to know about. And also, I mentioned here the Morehead State ground station. We also learned some things by flying that we really probably couldn't have figured out any other way. And a great example of that is that the actual location in a reference frame of where the Morehead State ground station, Morehead State, has taken an older dish and has upskilled it, added capabilities so that it could support deep space missions. The station hasn't been used, had not yet been used in deep space until we'd operated it. And so by using that ground station in conjunction with the other deep space network stations, we were able to very we were able to refine very narrowly the location that you put in an orbit determination filter for where that station is. And that our estimate was different than the published estimate that had been measured before, just using ground-based measurements. And so doing that analysis, we were able to update that so that the missions that were using Morehead State did not go in with that, what effectively would amount to an error in their ground station modeling for navigation. So when they launched and they started out communicating with the Morehead ground station, they were able to know pretty much exactly where it was based on the flight analysis that we had done. We also, through this, were able to quantify operational assumptions on things like link margins, how far into deep spaces we were heading out to 1.5 million kilometers, really understanding what was the data rates available, what were we able to get an actual performance of subsystems, communication subsystems specifically, that you can model them, you can simulate them in a lab at close distances, but really understanding how to validate those models in deep space was a key. And again, that allowed us now to think about future systems that we're developing with much better assumptions. So that was sort of some of the pathfinding lessons learned. We also, through the program, built several tools, so software tools, including a flight dynamics system that is optimized and is performing flawlessly in flying cislunar orbits, specifically these Earth-Moon 3-body orbits, which, it's not a lunar orbit, it's not an Earth orbit, it's a kind of hybrid of the two. That presents some unique challenges that we've been able to work through, and now have that as a capability. And what I mean by building them to scale is that this is now a capability that, yes, we're using for CAPSTONE and demonstrating on CAPSTONE, but now it's something that we're able to use to support other programs. And we have several other programs in development that now don't have to go spend that non-recurring engineering to build systems, and they don't have to spend a lot of time and money to test those systems because we are flight testing them right now. And also, in terms of tools that we've been able to build in the program, one of the key things I mentioned is taking commercial subsystems and systems that are built to fly in low Earth orbit or in geo and customize those for the moon. And there's several considerations that are not something you have to worry about. An example being in low Earth orbit, you can use, for small spacecraft, you can use torque rods in the Earth's magnetic field to desaturate reaction wheels. At the moon, unfortunately, we don't have that luxury, so we have to now have subsystems such as a propulsion subsystem that's optimized to take out and do momentum desaturation burns. But you can't just do that in a way that imparts a lot of translational delta V or impulse on the spacecraft, because these orbits are relatively sensitive. So if you do that inefficiently, you're now basically maneuvering out of the orbit that you did all this work to get into. So there's a lot of these requirements that they seem trivial. It's like, oh, easy to do a momentum desaturation, but when we really start to get into the details, it becomes a very complicated situation. And then finally, infrastructure and lessons learned are some key things coming out of this. So are doing our cross link with the Lunar Reconnaissance Orbiter I mentioned, a variety of technical challenges and also regulatory challenges with figuring out how to do these type of operations. And then also fundamentally, we see that as a foundation for navigation and communications in the future. So as people envision, relay communication satellites at the moon or navigation satellites at the moon, these are a lot of the things that we needed to uncover by going and making the applications to the regulatory bodies, by flying, by trying to do things at the moon and learning, what's achievable and what's not. And as I alluded to earlier, one of those key pieces from our perspective is the Cislunar Autonomous Positioning System, or CAPS. And so this is something, as I was working on my PhD at the University of Colorado Boulder, was really understanding that flying these missions, especially in multi-body, 3-body orbits at the moon, it requires a fair bit of navigation, which is not unheard of. But thinking forward and saying, okay, right now we have a few satellites at the moon. In 10 years, what might that look like? And so if we take a view that we're sort of in this renaissance of lunar exploration, development, and hopefully people living and working there, we see that in 10 plus years, we're going to have dozens of missions operating. And what we saw from that mindset is that the systems that we're using today, these point solutions from one ground station to one satellite at the moon, become fairly limiting. We have to then build tremendous amount of ground infrastructure to continue to support these systems. So the idea then was, well, why not try to develop something where we could have more of a peer-to-peer navigation system where spacecraft that were maybe already talking to each other already to relay data could also figure out where they are. And that allows then, we think, to optimize ground segment usage to get the data back from these missions, which is really what we're sending the missions there for, as opposed to spending a lot of time doing more routine housekeeping type activities. And so this is something that we're demonstrating on the CAPSTONE spacecraft. And our goal here is really to enable scale, to enable future missions. And also, just like we've seen with autonomy in low Earth orbit, if the spacecraft itself can have knowledge of where it is, this allows us then to think about autonomous operations on the satellite. So potentially in the future, we could have satellites that can figure out where they are, can plan their own station keeping maneuvers, and then basically just tell the ground operators what they're planning to do. Certainly, the ground can always intercede, but the idea here is that we can reduce the operational burden for operating these satellites at the moon, similar to what we've seen people do in low Earth orbit and in GEO. So I mentioned, our baseline data for this is a cross link, so the satellites are talking to each other. During the program, we also came up with had a realization that there are other ways we might be able to demonstrate some of these enabling capabilities. One of those was to incorporate on the program a one-way ranging experiment. And this, just to be clear, is a one-way uplink ranging experiment. So the Deep Space Atomic Clock, a program run by NASA a few years ago, has demonstrated a one-way downlink where atomic clock on board sent a timing signal to the ground, and then the ground used that one-way measurement to track where the satellite was going. And certainly we have atomic clocks in GPS satellites. The key here was to incorporate a chip scale atomic clock, very small form factor, really a chip that is certainly not as capable as a GPS clock, but much better than a traditional timing source for a flight computer, and basically add this to our radio. This helps us in two ways. One is in Earth orbit operations today, most spacecraft can use GPS timing. Even if they're not using it to know where they are, they use that to discipline their onboard clocks. Obviously, in deep space, we don't have that. So one way to use a chip scale atomic clock is to discipline onboard clocks so they don't drift. So you can kind of keep them in some sort of control. But the other, which we're really excited to demonstrate in the next couple of weeks, is a one-way ranging experiment where the ground will transmit a signal, timing signal. The spacecraft will receive that timing signal, and then the spacecraft itself will do the calculations to figure out its range from that ground station. This is a collaboration that we've done with the Jet Propulsion Laboratory, who developed the IRIS interfaces to the chip scale atomic clock, and then tested the ranging function through the ground segment and make sure that worked in the firmware of the radio. But that is only half the problem. So this will provide right now what JPL has developed, and what we'll be demonstrating would give you a range measurement to a ground station. And what we've been developing as part of CAPS is the one-way ranging navigation measurement processing. And so this will take those measurements, and then calculate a state estimate using them, which means we have to be able to do things like atmospheric corrections and other stuff that doing those things on the ground, not so hard. We've done them a lot. Doing them on board a satellite presented a lot of new challenges. So the second data type for CAPS that we're very excited about. And ultimately, as I alluded to at the beginning of this part of the presentation, we really are building this as a way to increase support the increase in frequency, duration, and complexity of future missions at the moon. So we see this really as something we hope will enable missions. Certainly big flagship missions will have plenty of ground resources allocated to them, as they should. And so what we're really thinking here is that this is something that will hopefully make those missions better, but really will enable smaller missions, commercial missions, other missions that perhaps when push comes to shove for resource allocation are not going to elevate to the level of certainly that they shouldn't elevate to the level of like a crewed mission to the surface, but nonetheless can help support the exploration, development, and settlement at the moon. So this is really what we're all about with this technology, is building for the future. Now, just kind of in closing, and then hopefully we'll have plenty of time for questions. Some of the challenges that we ran into for the mission, not really in any sort of priority order, but just things I thought might be interesting to talk about. One of those was parental leave, something that was not in a risk chart when we started the program, but just in the nature of the people that were involved. We had several key people, including myself almost twice, that over the life of the program had to juggle new family additions and the program's aggressive development schedule. The initial contract was raced between signing the contract and my second son being born, and then the launch was a race between my third son being born and getting to the launch pad. And so we had folks at NASA who had leave, and other partners. And I put this out there just to me, as an interesting observation, that as we think about rapid programs in the 2022, 2023 timeframe, this is a challenge that we had to address. And I think I was very proud of how we did address it. People took the time they needed, things got done, and we really didn't miss a beat because of it. But I think it's sort of a interesting point to highlight. As I mentioned earlier, certainly this story can't really be told without mentioning the global pandemic that hit the world really immediately after CDR. This caused a lot of knock-on effects. I mean, all the way down to literally the guy who needed to machine the tank got COVID, and that became a critical path item because he couldn't go to the machine shop to do the job. And really things that were nowhere near a long lead list became long lead because of impacts from the pandemic, whether that be on things like circuit boards or again, machine shops or what have you. So that was certainly a challenge. But also something that we learned from as it related to some of those analysis of alternatives and making a design that was resilient to changes. We also, in the program, had a pretty significant change where we originally baselined to launch out of Wallops, Virginia. And during the program development, for a variety of reasons, ended up shifting from Wallops to Mahia, New Zealand. And as you can imagine from a program perspective, it's a lot different to ship a satellite from Southern California to Virginia than it is to ship from Southern California to New Zealand. And also from a orbit design perspective, significantly changed the starting point that we were going to have to launch to space from. But in that way, actually showed the resilience of our transfer approach with the ballistic transfer, because we were able to maintain that flexibility, and we really can maintain that flexibility from any launch site using that approach, which is certainly much different than if we had been launching on a direct transfer, where the inclination on the launch site has much more impact on performance. Also, just over a year ago, we had here in Colorado the Marshall Fire, which burned about 1,000 or more than 1,000 homes in our community. Really, the majority of our team here at Advanced Space was impacted in some way. Fortunately, nobody lost their homes, but everybody, myself included, were evacuated from our homes and had to deal with a lot of different things. So that's certainly a curveball in the program we were not expecting. And then as it relates to the spacecraft operations, I mentioned we got to the launch pad. Very exciting launch on June 28th. And then fast forward to July 4th, I mentioned we separated from the upper stage of the launch vehicle on our way to the moon, and had our first exciting moment of flying a satellite when a commanding error was sent to the spacecraft, and the spacecraft actually stopped talking to us. Basically, somebody, there had been a mistake, and we locked up the radio. And so therefore, we could not we couldn't get any commands into the satellite. We couldn't get any data down from the satellite. And of course, this happened like the evening of the 4th of July. So we, yay, we separated. All's good. Going down to the campfire to celebrate the 4th of July, and all of a sudden, phone starts ringing, and we can't talk to the satellite. Something's wrong. It was very stressful a couple days as we worked through this. And one of the interesting side notes here was, as we were having issues, every single major news network in the country wanted to run this as a lead story, and we got it all lined up. The NASA folks were going to support it. It was going to be, we're going to talk about the challenges we were having and how we're working really hard to recover, which was great. We recovered the spacecraft, fortunately, got control of it again. And the second that happened, Nobody wanted to write a story about it. No one wanted to do interviews. Everything got canceled and it was all changed. So we learned really quickly that, failure is a lot more interesting to certain folks than success. I thought it was a much better story that we recovered it. But the media partners didn't, in general, agree with that. So we got the spacecraft back under control, did our first couple maneuvers. All was good until September 8th. We had just completed a trajectory correction maneuver. All the data looked good. Things were, we thought, proceeding well, and we saw the slightest little spinning signature in the signal that we were getting from the satellite. I mean, really just a small little blip. And we said, that didn't look quite right. Let's, get some more time from the ground stations, try to get some data on what's going on. We later found out that at the end of that maneuver, one of our thruster valves, one of our 8 thrusters, one of those valves had remained open, and it spun the spacecraft up, totally out of control, oriented in a way that we were not power positive with the amount of power the spacecraft was drawing. So by the time we were able to get data on the spacecraft had been dead banding. Basically, we were charging up just enough to send a signal, and then we would run out of power as we were spinning pretty rapidly. The thermal environment of the spacecraft, the propellant had frozen in the tanks, and we were able to, with pretty heroic efforts over about a month, using the 70-meter dishes of the Deep Space Network to get signal from the weak signal that we were able to get. We were able to understand what's going on, get commands into the spacecraft, stabilize the spacecraft, stop it from spinning, and ultimately recover it in time to do the near rectilinear halo orbit insertion. So quite a dramatic event there. Ultimately, the control system for the thrusters had to be rewritten. The valve is still open, so every time we do a thrust, we get a little bit of a disturbance, but has thus far been mitigated, and we're under control now. So these have been some very exciting lessons to learn, would maybe be the positive way to spin that. And finally, in closing, and then hopefully we'll have plenty of time for questions, I really also highlight, like I mentioned before, it's really a team effort, certainly with the NASA team that was supporting us, the Space Technology Mission Directorate, specifically the Small Spacecraft Technology Office program, and then all of the technology that went into the CAPS development, as well as the actual CAPSTONE program itself. It's an SBIR, part of the Small Business Innovation Research Program, which is managed by NASA Ames Research Center. The Artemis Campaign Development Division within NASA's ESDMD. It was a critical partner from the beginning of the program when it was Advanced Exploration Systems Group, and also has remained such. NASA's Launch Services Program over at Kennedy Space Center purchased a ride from Rocket Lab and managed that whole process. Very unique challenges that we had there with small spacecraft and small launch vehicle going to the moon. And then finally, from a NASA perspective, the Deep Space Network, I mentioned during our anomaly resolution, absolutely critical, but really throughout the whole program, incredible partners, incredible team at the Deep Space Network. So from a NASA perspective, that's who's helped us get it done, supporting advanced space and executing it from the sort of industry side. We had Terran Orbital, who is our bus and spacecraft manufacturer. Stellar Exploration developed a propulsion system, and they actually developed it during our program to fill one of those issues that I mentioned, except for the valve issue, which we think is a FOD issue. Propulsion system has been incredible. Orion Space Solutions was the provider of the integration chip for the chip scale atomic clock. So that's something we're looking forward to, again, demonstrating in the coming weeks. I mentioned Rocket Lab, which was our ride to space, the Jet Propulsion Laboratory, both as it relates to the Deep Space Network, but also as it relates to the Iris radio and some of the customization that we've done there. Designed by JPL, but really delivered through Space Dynamics Laboratory at Utah State. And then finally, I mentioned earlier, Morehead State University, who had the new ground station that we've been able to qualify. And finally, Tethers Unlimited, who provided the crosslink radio that will allow us to do the crosslink with the Lunar Reconnaissance Orbiter. So with that, I think I'm done. Love to open up to some questions, and I'll look to Lisa for how you want to do that.
All right. That was fantastic. Thank you so much, Brad, for presenting all of that information. I took a lot of notes. I don't know about anybody else. I have been checking to see if anybody posted any questions in the chat. I'm not seeing any questions in the chat. So if we want to go ahead and unmute phones, do use the reactions to raise a hand, so we don't have everybody talking over each other, and we'll try to take some questions. All right, Tom.
Thank you. Very, very impressive. Technically, managerial wise, what you've done. I think one of the really interesting things was all the challenges and lessons learned. Those are the kind of things people don't think about, but you technologically and management, you guys did a superb job. Question, you talk a little bit about your business plan. Who's your customer? What you can tell us about, you got 45 employees or 45 team members. How does all that pan out, and how are you keeping your head above ground that way?
Sure. Yeah. Thank you for that question, and thank you for the compliment to start it off with. So from a business perspective, for Capstone, primary customer, that was actually NASA. I mentioned we sort of had an interesting contract where what the NASA team really wanted was the lessons learned and experiences of doing this. So instead of going out and buying a satellite program, they went out and issued this contract to us, where it was a firm fixed price, milestone-based contract, really for the data that we were generating. So in that case, obviously Capstone primary customer is NASA, but because it's a commercial satellite, we're able to think about other technology development activities or demonstrations that we are, once we get through some of the NASA focused activities, certainly we'll add to that. More broadly, I mentioned kind of the three areas of our business: flight dynamics, technology development, and rapid turnkey missions. We would put Capstone in that sort of third category, right? So the end-to-end mission piece, where we're going out, figuring out what needs to be done, finding the right partners, and pulling it together. We have another program we've announced in the fall we're very excited about, called the Oracle program, which is supporting the Air Force Research Laboratory, which is effectively about a 10 times bigger satellite than Capstone, which will be using all our lessons learned from Capstone to go deploy for the Air Force Research Lab as a space situational awareness mission, where we'll be basically flying 2 telescopes to track objects in cislunar space. And so that is a major follow-on for us. Again, I mentioned about 10 times bigger satellite. That program is well underway. We have our system requirements review in about 2 weeks. So that's one other business way we've done it. We also provide solutions and services directly to the Gateway program. So obviously Capstone's informing it, but we have folks that are working with the Gateway team at Johnson Space Center every day, doing analysis and design work. And then finally, we have commercial customers and others that are coming to us for a variety of those solutions. So as a business, we've been growing profitably. I guess I should also caveat in this era that we're in, we haven't raised outside investment capital. We kind of control our speed and our priorities and align those with our vision. And all things considered, these have been going profitably and going well. I don't know if that got your question, sir, but hopefully it covered it.
Great answer. Thank you.
Yep.
All right. All right. We do have a couple of questions on the chat. They're both related to each other. So I'm just going to read them, paraphrase them a little bit. From James Ortiz. What is the plan for the end of mission? And then from Marianne Dyson, she's also wanting to know what is the limiting factor for the end of satellite life and where it will end up: purposefully crashed into the moon or left in halo orbit? If left in orbit, would it naturally decay to end up on the moon, and how long would that take?
Great questions. Yeah. So as you can imagine, the last thing I want to think about is ending our satellite with crashing into the moon at this point in time. But it is actually one of the interesting things that we had to think about before we could launch responsibly and be able to have this story well understood, just to get to the launch pad before we ever even got to space. So we have, from a process perspective, I'll start there. We have done an extensive report that we had to do consistent with the orbital debris guidelines, which are anywhere you go into space. Certainly the moon is a little different than in low Earth orbit, but we still had to do that. And then a planetary protection plan. And that relates at the moon to avoiding sensitive areas. Certainly we don't want to end the mission into a historically relevant site, right? So through all those activities, we had to do a lot of review, primarily with NASA, the regulators, to make sure that we were, we're not going to do anything that would be damaging to anybody else or to important sites. So with that said, the plan, when we get to that day, hopefully very long time in the future, if we're intentionally ending the mission, the baseline plan is to impact it intentionally on the surface of the moon. So it's out of the way. No one will have to worry about running into it later. But another option, which is sort of the second part of the question, is that it will actually naturally decay from this orbit. It's sort of a self-cleaning orbit. So if we were to do nothing in 10 to 15 weeks of time, depending on exactly when we let it go, assuming we did no maneuver, we would depart the orbit. Of the majority of those departures either impact the moon or go out into deep space, both of which would be sort of compliant disposals. If we were to do a maneuver where maybe we didn't have enough fuel or for whatever reason we couldn't target an impact, we could target a departure burn that would accelerate that and make it much quicker. But at the end of the day, we want to get out of the way. Obviously, Lunar Gateway will be there in the coming years. So the key is naturally we'll get out of the way if we don't get out of the way on our own in the meantime.
All right, great. Thank you for that. There's another question in chat from Steve Schenfeld, and this is one that I wish I'd asked. You've gone from a development program to an operations program. How do you manage your skill set and experience gained in each to improve each of your next development and ops efforts?
That's a great question. Thank you, Steve. Yeah, so really the short answer to that is they're the same people. We're not big enough of an organization to have a lot of silos. So the people who are supporting operations of Capstone and who supported its development are now working on other programs like the Oracle program I mentioned for the Air Force Research Lab. And so a lot of that is inherent just because somebody did something a year or two ago and now they're doing it again. And I say sometimes we learn some pretty painful and expensive lessons. We kind of refer to those as scar tissue, and we try to avoid, having the same scar tissue twice. So a lot of it is just inherent in the small size of the team that we have, that they've done it before now for Capstone. They're doing it again for other programs. The other one that we do is even if it's not the same person, we even at 45 people, we really try to foster a really open and flat kind of organization. So even if it's a different person doing it, we have this sort of very open dialogue amongst the team members, so that hopefully what I request people to do is if they're going to make a mistake, I'd like them to make a new mistake and not make the same mistake we made on another program or another thing that we did.
All right, great. So from David, did you use any AI or other generative design techniques for development? If so, for what was it used and what tools did you use?
Great question. So for Capstone itself, let's see, I don't think we had any like design tools that were AI powered, but we do have several technologies we're developing with NASA under SBI and otherwise that are looking at deploying neural networks onboard satellites to enhance automation, specifically in the Earth-Moon system, and specifically as it relates to things like station keeping and electric propulsion. So we have another program. It's called NEP, NNEP, neural nets. For neural networks for electric propulsion, and we joke that's called the neural nets for everything program, because we can basically take the same approach, train neural networks on the ground, deploy them on satellites, and get enhanced performance. But as it relates to the development program, we did not. Although I guess I should say we have looked into some natural language processing type tools that would help us to better manage documentation, lessons learned, and operations. But right now, the benefits of that, really hit when you scale to a lot more people than we have right now.
Okay, great. All right. So Bill Davidson asks if you could talk about station keeping.
Absolutely, yeah. So the orbit we're in at NRHO, our plan had been, we call them orbit maintenance maneuvers, or OMMs. Our plan from the beginning, we'd assumed we would do about one of those a week. And that really just gets to keeping If you kind of think of there's a reference orbit that we want to be in, those orbit maintenance maneuvers really just try to keep us close to that reference. As we have flown it, a combination of things have actually meant we have done them far less often. So I think we are in our 10th or 11th orbit, and I think we have done 2 OMMs since we've gotten there. The key drivers there, one is things have been behaving, if you will, dynamically better than we assumed, and so the dispersions have been reduced. But also because of the thruster valve issue that I mentioned on our way to the moon, we've actually increased the threshold. So instead of doing a small maneuver that would potentially create error because of this thruster anomaly that we had, that we'd have to correct, basically of the same order of magnitude as the orbit maintenance maneuver. So we've raised the threshold so that we're doing fewer larger station keeping maneuvers or OMMs in order to mitigate that thruster valve risk. But thus far has been performing very well, better than expected. And as it stands right now, based on the program, we do not believe we will be fuel limited in our operations. We'll most likely be component limited as we get into the future and systems start to degrade over time.
Okay, thank you. Stokes also has a question, actually 2 questions. What type of contracts do you have with NASA? And what is CAPSTONE's weight and thrusters thrust? That's 3 questions.
Well, that's great. And getting into technical things that I have to go try to remember off the top of my head on that performance stuff. Stokes, you're killing me. But as it relates to the contract itself, it's a firm fixed price milestone based contract. As we have had the development of the program and now operations. And it's actually structured, which I think is kind of interesting from a wonky perspective. This probably tells you why I don't have the performance numbers off the top of my head. It's because I think that's interesting. But it's a phase 3 SBIR. So as it is employed, this really is a small business and research contract, and it is configured under those protocols. I'd have to get back to you on the thrusters. It's pretty small, to be honest with you. So we're talking about the thrust chamber head is basically the size of a pin, a pen head, and the FOD that we're looking at is incredibly small. The part of the challenge that we've had is that we maybe think we brought prop systems have maybe gotten too small, and that the reasonable cleanliness that we could achieve, we might have exceeded that, since we thought we had locked everything down from a FOD perspective, but right now we believe the FOD is in the valve. So I don't have the other numbers off top of my head, but pretty small thrusters. And actually one of the challenges for other programs that we're developing is the minimum impulse bit for the thruster is actually a key consideration for these orbits, because in a perfect world you would do really small station keeping maneuvers, again minimizing your uncertainty and your errors, and then we've seen some systems where you just take a off-the-shelf thruster and try to use it, and you actually end up with thrusters that are too big and make it hard to stay in the orbit. So sorry I don't have those details on me, Stokes. I closed all my other slides so I wouldn't delay things on the presentation.
Well, okay. Great answer anyway. Thanks a lot. So you don't have a Space Act agreement?
No, we don't. Everything has been through the SBIR contract. Yep.
Okay. Do we have any other questions for Brad this afternoon? I think everybody has control of your own microphone, so I think you can unmute if you do have a question, or you can type it into chat. All right. So another one from Steve. I'm guessing you don't have the ability to get this sort of data, but was there any consideration to get mission data on any sort of propulsion byproducts from previous burns perturbing your orbit or prop use?
So I'm trying to make sure I understand it right. I mean, what we have done in operations is book kept both on commanded as well as accelerometer based measurements to accumulate how much fuel we have used. But I'm not sure about we didn't have any sort of sensors for byproducts or anything like that, if I'm misunderstanding the second part of it. But we have a spreadsheet, so we have a good idea how much fuel we have left.
Okay, Steve, do you want to clarify or ask a secondary to your question? I'll take that as I'm really asking about your next time through that orbit. Yeah, so each time you go through the orbit, are you able to determine any kind of propulsion byproduct prior burns?
Not chemically, but dynamically, as the further we get through the specific orbit, the better orbit fit we have, and so we're able to go back. We know what we commanded. We have timers on board and we have accelerometers, but then from a dynamics perspective, we're also able to go back and estimate the maneuver in our orbit determination filter. So that's one way to understand exactly. We think we know what we did. We measured it with accelerometers, and then we can do our orbit determination solution, actually solve for it. But as it relates to sensors for byproducts, there isn't anything on the system right now for that.
Okay, very good. All right, last call questions for Brad this afternoon. He's already got one homework assignment from Stoke.
I'm sure it's on our website, Stoke, so Google probably would tell you quicker than I can. Sorry.
Okay, I'll look at that. Hey, Brad, I'm impressed that you've done so much with such a small team, and now you have the Oracle thing going. You guys must be working 24 hours a day.
It feels like it sometimes, yeah, no, but it's been good, and a big part of it is really we try to focus in on what we're good at. Right. Well, I guess I should have been clear. We don't build satellites here. The only thing I tell people we build here is Legos. We have a great Lego collection in our lobby. But really, we're building the software, the tools, the designs, and then going out and having great partners like Tyvak or Terran Orbital for CAPSTONE out in Southern California, building small spacecraft. And then for Oracle, a partner for the spacecraft part is General Atomics. And then they have a great sensor provider in Leidos. So we're really leveraging, what people are good at. And one of the things that helps keep our team small is that we're not trying to do everything for everybody. We're trying to focus on what we are uniquely capable of doing. But yeah.
All right, wonderful. We do have a comment from Steve. He'd like to thank you and your team and the mission and for presenting this to us. I'd like to echo that sentiment. This has really been a lot of fun, very informative. Really appreciate you taking time out of your day away from the kids and the raging fires and the snowstorm, freezing cold weather, stuff that goes along with living in Colorado. So really do appreciate, and I appreciate everybody online. We had a lot of challenges with getting Zoom to work for us today. So my apologies for that. We're trying to figure out why you got a bad link. We'll try to get that corrected in time for our next meeting. Just a reminder to everybody, the video recording of today's presentation will be available on the NOW website in a couple of days. So be sure to look for that so you can hear anything that you didn't hear correctly the first time, or if you missed a portion of it because it took a little while for you to get logged in, the recording will be there. Our next First Thursday meeting is going to be on March 2nd. It's the wonderful thing about February only having 28 days. So March 2nd will be our next meeting. The details of the program will be announced at a later time, but that meeting will be in the Lone Star room as well as on Zoom. So hopefully, especially for everybody in the Houston area, you'll be able to join us in person. And for those who just hate to make that long drive to JSC, you can join us on Zoom. So Brad, thank you very, very much. Really appreciate your time and your flexibility with being able to join us today. And we'll just go ahead and wish everybody a happy rest of the afternoon, rest of the evening, and look forward to seeing you all next month. Take care.
Great. Thank you, Lisa. Thanks, everyone. It was a pleasure.